first, just get the notes there. Missed the first bit of the lecture on the recording, but we'll pick it up here talking about orthographic projection. So looking at this diagram here, we can see these dotted lines through the diagram. So these are joining each point in the aligned world space with their image under the projection. Okay, and these lines are called the projection lines or the projector lines. Okay, and these are all meeting the XY plane. They're all intersecting the XY plane in the projected points, and they're all meeting the XY plane at a right angle, aren't they? Okay, because they're all parallel to the Z axis. Okay. Now we'll meet in the other type of projection, perspective projection, we'll meet these projector lines again, and they'll be useful concept to talk about. Now one important property of orthographic projection is that all objects retain their original size in a way, okay? No matter what their distance from the viewpoint, okay? So this arrow or this kind of house type object here, you know, is rendered as a certain size in the projection. Of course, now it's presented parallel to the XY plane, so you kind of see it in the same size, if you like. Of course, if it was oriented differently, if it was slanted, so it wasn't face on to the camera, but it was slightly slanted, of course, the projection would be a lot narrower. But the point we're making here is that the size of the projected image doesn't depend on the distance from the camera. So a same sized house a million miles away, a million miles down the Z-axis, under orthographic projection, it would still arrive on the XY plane looking like this, the same size, okay? Now that is kind of simultaneously an advantage and a disadvantage for this projection. It's an advantage in the sense that the size of the object in the projection is, you know, corresponds precisely with the actual size of the object in reality. So things in the projection have the same size as they do in reality. So that can be an advantage. It's a faithful representation of the object in that sense. However, if you want your 2D image to be to create the illusion of reality, to create the illusion of an actual view of the scene, then it's also a disadvantage, because we're all used to the fact that things in the distance appear smaller than they are than if they were up in front of your face, of course. Okay, so that disadvantage, I think that yeah. So we lose the information about depth. Okay, things that are far away from the camera and things that are near from the camera are rendered in the same way, are projected in the same way onto the plane. Okay. So that's a disadvantage if your aim is to create a realistic looking scene, okay? To create the illusion of a three-dimensional, you know, that you're actually looking at the scene, okay? But some other properties which might be advantageous about this projection is lines that are parallel in the world space are still parallel in the projection, okay? So these two, you know, for instance, the bottom line of this house here, and maybe the top line going across the first floor, no matter how the object is oriented in the aligned world space, lines that are parallel in the world space, when they undergo orthographic projection, they'll be projected to lines in the screen space or the projection space that are still parallel. So this projection preserves the parallel relationship that might exist between lines. And for that reason, you know, you can also think about that as that the projection isn't changing angles. So the angles that you see on the projected space are a faithful representation of the angles that exist in the actual 3D environment. Okay, so you can often measure angles accurately on the projection, and they'll correspond to the angles in reality in the 3 dimension. And for that reason, and the reason that it preserves size, It preserves parallel lines. These orthographic projection is often used in technical drawings or architectural drawings. Sometimes you see architectural drawings, say of a, well, just say of a building or a new extension to a house, or maybe even a large development consisting of many buildings and tower blocks and so on. Technical drawings are produced of the views of the arrangements of these buildings from various angles, and often they're using orthographic projection. So if there's many houses and many buildings in the scene, a drawing is produced which doesn't contain any perspective information. So buildings that are further back in the setup are kind of drawn on the thing at the same size as buildings that are nearer, okay? Because the object of the technical drawing might be to give, you know, from that orthographic projection, you can see objects that are the same size in reality are rendered the same size on the drawing, okay? So you can directly compare the sizes of different objects, even though it mightn't be immediately apparent how far away the objects are relative to each other, okay? So you're losing depth information, but you're retaining a lot of actual information in terms of the sizes of objects and angles and so on, okay? Now, before we get on to, I mean, our main concern, and, you know, if you're thinking of the use of computer graphics in computer games or, you know, virtual environments like that, the orthographic projection isn't really used. What is mostly used, or almost always used, is some kind of perspective projection. So the objects that are far away do indeed appear small, to give a realistic representation of the scene, okay? Now, but before we get on to that, we'll just look at a slightly related projection related to orthographic projection. This is called oblique projection. So oblique projection, now I don't have a diagram to kind of show this, but oblique projection is where, well, the projector lines are still all parallel to each other, okay? Let's draw a suggestive diagram. So let's just draw a top view of the environment. So we're seeing, let's say this is the x-axis and the z-axis. So the y-axis is perpendicular to the plane and coming out at you. So here's the z equals 0 xy plane represented as this line here. There will be an object in the environment, but oblique projection is when, well, let's draw it down here so I'm not going off my diagram. Oblique projection is when the projector lines are all parallel to each other. So these would be the projections of the four vertices of this, or the four vertices of that object that we're seeing here in the scene, but they're no longer parallel to the z-axis, okay? So it's no longer a perpendicular projection onto the xy plane, but it's oblique. It's at a slant, at an angle, at a non-right angle. Okay. Now we're seeing the top view of it. So this shows us that the projection vector, if you like, or the projection direction is not parallel to the z plane, and it may even have some height to it. We're not saying that the projection vector necessarily is parallel to the ground xz plane. It could have a certain pitch to it as well, and that's important because one of the things that oblique projection can do is it can take the original x-axis that was in the original world space, and through the use of an oblique projection, you can send that original x-axis in the environment onto the x-axis of the screen space. So, and that can be useful in producing certain kinds of projections. Because remember, if you think back to the alignment transformation, when you align the world space to the position of the camera in the viewing direction, that involves two rotations, a yaw rotation, rotating about the y-axis. Now, rotating about the y-axis, the original x-axis will rotate, but it'll still stay parallel to the x-axis of the screen space. It won't get a tilt to it. But the second rotation involved in alignment, which brings the center of view down onto the z-axis, that, if that's a non-trivial rotation, that will tilt the original x-axis of the environment, tilt it relative to the x-axis of the screen space. If you just use plain old orthographic projection then, when that is projected to the screen, that original x-axis, which is the kind of horizontal axis in the original world space, that will be slanted on the screen, okay? But through the use of an oblique projection, you can do the projection at such an angle that that tilted x-axis is again brought to be projected onto the x-axis of the screen space, okay? So you kind of straighten everything out again, so that the horizon of the original scene will now be the horizontal direction of the screen space. So in terms of matrices, how would you actually implement such a transformation? Well, we're still projecting onto the xy plane. So we're still going to produce a vector with 0 z coordinate. That's why you've got this 0 third row in the projection matrix. But we're going to do our projection along some projection direction d. So d, this direction here would be this d vector, the projection direction. It gives the direction of all the projector lines. So d will have coordinates dx, dy, dz, and the correct transformation matrix that we want to use is this one, okay? So we have, in that third column there, we have these quantities, minus dx over dz and minus dy over dz in the first and second entry there, respectively. So, well, let's just go back to our diagram and just confirm those are the correct ones to use. So let's just take one of these points here. Now, if this is the vector d, that's the projection vector, or at least that's a top view. So here I'm looking at the z-axis there and the x-axis, okay? So the y, so we're looking down, so we're seeing the screen is just this, the screen will just be represented by the x-axis here, okay? So you're looking at a top view of the situation. So the screen is coming out horizontally here, and you view it from below, if you like. So this is the projection here. So given the x coordinate of this point, the idea would be what is the x coordinate of the projection at that point onto the screen. Now here's the projection vector d, and which bits of d can we see accurately? Well, this distance here will be exactly dz. And this signed distance here will be dx, okay? Now, actually, as it's drawn in this diagram, both dx and dz are negative, okay? Because the vector is going down and to the left. So it's a vector with negative z and x components, if that's the positive x direction, and that's the positive z direction. So the question is, how far do we travel along here, along the x-axis, by the time this projection line intersects the intersects the x-axis at z equals 0. Well, you can kind of think through this. You can think of x prime as starting at the x coordinate, and we're going to be adding on a certain multiple of this quantity dx. You can think of it as kind of stepping left a certain number of times, and the number of times you're stepping left will be determined by the number of times you have to step down. The number of times you have to step down in order to hit the screen in perpendicular projection. So if we let little z be the z coordinate of this point, what we'll need to be doing is dividing z by dz and taking that amount of multiples of the quantity dx, okay? And we'll have to be subtracting that, okay? So dz and dx are both negative, as we've said, as I've just chosen to draw the picture there. This z quantity is positive. So if we want this proportion, if we want to grab this number of steps, okay, which could be a fraction, you know, that there might be 2.5 steps down here, we need to divide z by dz, by the dz component of the projection vector d, and we'll need to subtract it because we want to go down in that number of steps. It's in the opposite direction of this positive z coordinate here, and you're taking that amount of multiples of dx. Okay, and similarly, if you look at a side view of the projection thing, so if you then draw a picture of the side view, which would have the z-axis here and the y-axis here, and think of projecting the point obliquely down onto the y-axis, you'll find that y prime is going to be the original y-axis of the point minus z over dz dy. And these values agree with those produced by the given matrix in the notes. If you look at that given matrix, the given matrix in the notes was the matrix with minus dx dz 0, minus dy dz and a 0, and then a 0, 0, 0, 0, 0, and a 1, 0, 0, 0. That was the projection matrix given in the notes. So when you multiply that by the general vector, which is this is the position vector of the point out in the 3D environment. So the position vector of this point out, that point there, this matrix multiplication should give us the coordinates of the projected point. So this point here, or equivalently that point there in the side view. That's the side view, and this is the top view. Well, when you carry out this matrix multiplication, multiplying the rows into the columns and that, you see the first entry is indeed x. Well, because of the minus sign there, you're going to have minus dx over dz times z. And the second coordinate will be y minus dy dz times z. The 0 row here will produce a 0 entry for the third entry, and then you'll have the last homogeneous coordinate. Okay, so we do get exactly these values here. from the matrix multiplication. Okay. So that's a derivation of that oblique projection matrix, if you like. So, okay, any questions about that? So, as we said, one advantage of this is that if you can choose the projection direction vector D so that it projects the original x-axis of the world space onto the x-axis of the screen space. Okay, so although things get tilted in the alignment transformations, you can undo that to some respect, and in the oblique projection of the environment, the horizontal x-axis will still be horizontal on the screen. Okay, things will be distorted in other ways because of the obliqueness of the projection. But if you wanted to get the horizontal direction on the horizontal direction of the screen, that can be achieved using an oblique projection. Now, of course, oblique projection still loses all the depth information. Okay, so objects, the same sized object in the environment placed close to the camera and far away from the camera, they will still be projected to be the same size on the screen space. Okay, which is kind of simultaneously an advantage. The same size things look the same size on the projection, but it's also a disadvantage because you lose the sense of how far away they are from the camera. Okay. So we come now to perspective projection. So this is kind of, for the purposes of like computer games and creating a realistic view of the environment, this is of course seen as the better type of projection to do. Okay, because it retains the depth information. Okay, so we all know, students in the front row appear a certain size to me. Students in the back row, okay, I know everybody's the same size roughly, but the students in the back row look kind of smaller because they're further away. Okay, not so much in this small room, but in the large lecture theaters, it's more pronounced. So so that's an important aspect of reality. I mean, if you look historically, it did take artists, it did take them some time to figure that out and treat perspective systematically. If you look back into the history of art, the earlier paintings, people seemed a bit confused about how to do perspective correctly. And you can look at old paintings. I don't know enough to tell you from exactly what periods, but looking at older religious paintings, because most of the Western art anyway was kind of produced on religious themes, but often the projection looks all kind of screwy. It's not done correctly, and things that should be in the distance of the scene are kind of, in strange size in the painting. Okay, and things don't look right in terms of how things disappear. Even when they started to try and achieve a view of perspective, it often isn't done correctly. Okay, so it took people a bit of a time to figure this out correctly. And has everyone seen this episode of Father Ted? Do you know about it? Some people don't know about it. Does everybody know what Father Ted is? Everyone, yeah. So it's a comedy about these Irish priests who have been exiled to this island because they're all kind of crazy in various ways. But this is Father Dougal. He's the simpleton character. He's like a child figure. He doesn't really know how the world works. And this is Father Ted, who is a bit more clever. But they were on holiday one time, and they were stuck in this awful holiday park in this horrible caravan in terrible Irish weather. And they were stuck there for days and days and just bored out of their minds. And one thing that Ted tried to do is he tried once again to explain the notion of perspective to Father Dougal, who didn't understand perspective. And so there was this famous line where he's holding up two plastic figures of cows, and he was saying to Dougal, okay, one last time, these are small, The ones out there we can see out through the window are far away, because like when you hold them up beside each other, they look the same size. The plastic cow is the same size as the, or it appears to be the same size as the cow out, the real cow out in the field. Okay, and the comedy was because Dougal just still couldn't grasp this. He just couldn't get his mind around this strange proposition. So this is the notion of perspective. Things in the distance are, if you want to produce a two-dimensional view of them, you should change the size. So the way this is achieved, let's have a quick glance at the diagram on the following page. So here's the viewpoint at the origin, and here's the object out in the scene. We also imagine a projection plane, okay? A projection plane which is kind of between the viewpoint and all the stuff in the scene. Although there could be stuff, there could be things in the, there could be objects in the world space that are in front of the projection plane as well. That doesn't really matter. And the basic idea behind setting up a perspective projection is just to emulate or just to simulate what's going on in reality. Okay, so what's going on in reality? How is it that I'm seeing in my mind some image of what's in front of me? Well, just take a few basic assumptions or some basic ideas. Light is a series of rays, and light travels in straight lines. Okay, so light is bouncing off all the objects in the scene, and it's entering into my eye and then gets somehow to my mind. But light is traveling in straight lines, and for the purposes of this discussion, you can think of my eye as just being a point object. Not exactly a point, because I do have a very small circle of your pupil through which the light is getting into it. But to set up the basic idea, you can think of your eye as just being a point object. So in order to get into my eye, to somehow make it through to my mind, the light rays have to hit exactly that point object. So the only light rays I'm going to perceive are the ones that are coming in a direct straight line from a point in reality, a vertex in the world, and going straight to the origin, straight to my viewpoint. All the other light rays I'm not seeing. They're bouncing off my nose or missing my head completely. Okay, I'm only perceiving the light which is hitting my eye exactly. So that's what we do. The projection plane you can kind of think of as, well, okay, the actual projection plane which is going on in the scene, of course, is your retina, which is behind the viewpoint, and it's also slightly curved, and the image that makes it onto your retina, of course, is upside down, because when you extend all these lines backwards a bit from the pupil backwards onto the retina, of course, the top of the house will be underneath the bottom of the house. So actually modeling what goes on in reality with your eye is complicated by that the retina is behind the eye, things get turned upside down, the retina itself is curved. So, you know, it's quite a lot of complicated geometry there. But to do the perspective projection, we can kind of simplify that by flattening your retina, if you like, and moving it to in front of your eye. That sounds kind of strange, but it does simplify the geometry a lot. So we have this idea of the projection plane. You can think of it also as like a sheet of glass or something. A sheet of glass that you're holding up in front of the scene. Now we're only perceiving the light rays, remember, that go straight from the vertex in the scene and hit my eye exactly. So these projector lines are the only light rays I'm seeing. So what we're going to do is we're going to track these lines and just record where they intersect the projection plane. And where they intersect the projection plane, that's the projected point I'm going to record, and that's the one that's going to be transferred onto the computer screen. Okay? So all the vertices in the world, they're projector lines, which are all heading to the origin. They're all the straight lines from the points to the origin. We're recording where they intersect this projection screen. Now, the projection screen is oriented so that it's parallel to the XY plane. So all we need to know about it is how far away from the XY plane it is. Just its distance from the origin, distance from the viewpoint. So for this treatment here, we're going to specify that distance as f. Okay. So we'll need to know that, because depending on different values of f, if you slid the projection plane forwards or backwards, well, if you slid it forward, that would produce a larger image of the house. If you brought it back closer towards the eye, see the size of the house, if the projection plane was down here, would be smaller on the projection plane. So all we need to know about the projection plane is just its distance f, perpendicular distance f from the XY plane, okay? Because we're going to use a projection plane which is parallel to the XY axis. Okay. Again, we're going to want to describe to retain consistency with the approaches we've done so far. We're going to want to use a matrix to carry out this projection. So to implement this method or to carry it out, what we want is some kind of matrix type method for taking the coordinates of these points in reality in the scene and obtaining essentially just the two-dimensional points, just the x and y points. That picture's a bit funny because they got the x and y axis there. I think that's a misprint. That should be the horizontal. Anyway, good about that. So we just want the two-dimensional x and y coordinates of the projected points on the projection plane. Now, this can't be produced by just a single matrix, unfortunately. So it's going to mainly be carried out through a certain matrix multiplication. But then also, we're going to make use of the convention for rendering points with homogeneous coordinates onto points with just normal coordinates, okay? Now, there's a bit of, I don't want to rush that, so we'll pick that up in the next hour when I see you at 11. And we'll do the treatment of that, of how you actually carry out the projection, and then look at some properties of it to do with vanishing points and so on. Okay, so I'll see you at 11.